Okay, looks like we are in business. This is KDM Stats, I guess my name is for this particular YouTube video. I'm making all sorts of YouTube videos these days. As you know, if you've been following along on my Patreon, I do have chronic fatigue and I am taking some time off. And I've been doing vlogs revolving around chronic fatigue on a different YouTube channel. And I've been thinking about making videos about doing computer games on a different YouTube channel. So all sorts of videos all over the place. But today, I only did the Mastermind framework yesterday, but I was playing around with it. As you can see the output here, I was actually playing a game against the computer using my physical board I've got here, this thing, and actually using that as a proxy and not having to fill in the secret code on the board because the computer obviously knows it. And obviously you just comment out this piece of this line, and then you don't know what the actual secret code is until you win. And what was really interesting is that it never took me more than 5 turns to win the game. I always won on turn 5, as long as I didn't confuse P and U, and then the computer gave me the wrong answer, and then that took a little bit longer. But if I played properly and I typed in the right thing, it always took me 5 turns, except once I got 4 yellow pins on turn 1, and then it only took me 4 turns. But yeah, 5 turns, and I think logically, with the colors are all different, if you enforce that rule, then it might be possible that you can code up an AI which will never take more than 5 turns, because AI is probably going to be smarter than a human. So anyway, what we're going to do now, oh, and I figured out why the bloody thing kept stopping. It turns out that F3 in Eclipse is the reference. So you go through to that class. And I knew that, and I was pressing it. I just wasn't thinking about it as I pressed it, because I've been programming for like decades now, and you know, you just do things without thinking. Didn't think about it. Turns out that was the same key that was doing recording stuff. And I got this stupid cough, and I don't know how to get rid of it, but we'll just have to deal with it. So anyway, what we're going to do in this one is we're going to start coding up some AI. Yeah. I want to get the AI framework, and when I say AI framework, I don't mean AI framework. I mean the framework that allows this to run like 100 times or 1,000 times or something like that. I'd like to get that done first, because I think that might be important. So what that means is that we're going to change all these system.printouts to go over to the log framework. So basically, we already got a print logs statement. So what we're going to do is we're going to, what are we going to do here? We still want to control everything from in here. So set print log. We're going to start off still keeping it human playable, but move over to the log framework. So here we're going to have, let's just start working here. Public void add log. So my idea is I want to basically I want the logs to be printed out if you're a human, but not if you're an AI. However, if you are playing an AI and you crash, then I want all the logs to be printed out. So we're going to need this, which is all logs dot add. I think this one adds to the end, which is what we want. A new log message, and if print logs system.out.println message. Okay. So that's fine. So that'll be for the stuff like the evaluation, and the turn log. This sort of stuff won't even get printed out if you're not a human, so we don't have to worry too much about that. So let's go ahead and let's search for system.out, and we'll see how many of these we need. Looks like they're all in there. Okay, so evaluation is going to be log handler dot get instance dot add log. Okay, it's basically the same thing. These are fine to add as leave as system out because they're just going to be user stuff. I think that's it. Why did it not find system.out resource? I got to make sure I don't set workspace, otherwise I'm going to start searching all the KDM stuff. Okay, log handler, print message. Okay, that one's fine. Log handler, mastermind run. Yeah, we better replace these. Because if we start running like 10,000 games, then we don't necessarily want these to be in there. We're going to need a clear logs here as well to get rid of all that. Now here's the one I was searching for. Turn. Yeah. Okay, so then we just got this and that and stuff. So I don't think there's a need to keep the logs for previous runs. So if you run it like 10,000 times, you don't need to keep the logs for all 10,000 times. You just need to keep the stats. Like the two stats are if you won or not and how many turns it took you to win. I think they're the only stats we really care about. So clear. So then we go into mastermind run and log handler dot clear logs. I'm not sure the logs will be that helpful with actually diagnosing problems. Run equals 0, run lesson, run count, run plus plus. We might have to put some more smarts in here if there are performance issues. I'm hoping there won't be, but yeah, we'll see how we go. Publish static final int run count equals 1. Set that to 1 for now. So let's go ahead and just see how this goes. So if we run mastermind run RYGB RYPU. Okay, so it's still printing out everything it needs to. So it could still human runnable, even though we've moved most of the printouts into this log handler. So if we go now to mastermind run and we set this to false, and then we run it again. See, now we're just getting the user stuff. And eventually this will just terminate and it won't tell you anything. So that's beautiful. So that means that as long as we're not actually using the human interface, then yeah, we should be fine. So let's start getting into the AI. So we're going to create a player controller in here. And what are we doing with the game controller? We're also going to create a package here called player modules. So the player controller is going to select a module, and depending on what that module is, that's going to be how the game works. So we're going to have private player controller and what are we going to have? We need we still want to control it for some level, so we're going to have an abstract class, I guess. So just going to check we're still recording. Abstract player module. I want to mess around with different types of AI as well. So we're going to have this framework is going to allow us to do that. So abstract player module. Actually, I should probably call that a player module. Just a little bit nicer code naming. You don't want really long names, and the abstract is kind of irrelevant. So then we're going to say player controller equals new player controller AI module. We'll call it player module because I'm going to put the human interface into this module as well. So we don't really want to say it's going to be AI because it is going to include the human interface as well. Now what we need as well is we need this. So player controller dot formulate guess based on the board. Okay. Create method formulate guess. Let's see. We want this to be an abstract. This is an abstract. Oh no, it's not an abstract, isn't it? It's not an abstract. What am I doing? Player module dot formulate guess board. Now, I think we just pass the board around all the time. We could store the board here and then rely on it, there only being one version of the board in the entire system. So we update the board in the game controller, and then when we reference it in the player module, it's the same board. So it'll have been updated, so we don't need to pass it around. But I'm going to pass it around anyway, just because, here we go, create abstract method. Just because it's safer. I don't have to worry about, you know, having the right version of it anywhere, blah, blah, blah. So now let's create a human UI module. And this one will extend a player module. Extends it. There we go. Add unimplemented method, formulate guess. And this is where we go and we yank this code out. Put this in the human UI module. Get guess input. So they both return combinations, so we can just whack this code directly in there. We'll take the comments as well and put them up the top. Scanner, next line. I did have to take the scanner, and what I did was I actually made it a static global parameter because I wasn't closing it, but I was creating a new one every time, and that felt a bit ick. But if you make it a static global, technically you're never closing it, but you're only opening it once, so I don't feel too bad about not closing it because it's like, you know, it's just global, who cares? Formulate guess. No, that should definitely be public. Are you going to complain now? You are. Okay, so formulate guess. Mastermind run. Okay. So we're going to say here, a player module p module equals new human UI. Actually, we're going to say null. If I'm kind of over engineering it here, but what we're going to do is we're going to create an enum. No, we don't have to go that far. We don't have to go that far. I don't want it to be a global variable because it might have parameters later on. So we're just going to say human UI module. And what we'll just do is we'll have like another line commented out for the player. And whenever we want to swap between them, we just comment this one out and then uncomment this one, and then we're good to go. So that'll be how we do it. So we've got the human UI module. Let's run this again. Let's remember to turn print logs back to true. Mastermind run. RYGB. RYGO. Okay, that seems pretty good. Still running. Let's just do a check with the secret code turned on. Just to be safe. BYUO. Done. Okay, so everything's still working. It's going through the player controller and formulating guesses. So now we've got this interface. Let's start getting into the UI. So human UI module. I think I want another package here. Player AI. And then we're going to start off with stupid AI module. This is just going to be a proof of concept mainly. So extends a player module. I don't know if we need a midpoint abstract class that represents an AI player module or an abstract AI module. I don't think so at the moment. I mean, it's just a simple method, so we're not going to worry about it. So what we're going to do here is return secret code utils dot generate random combination. Now we still got print on is true. So what we're going to do here is stupid AI module. Mastermind run. Okay, so it doesn't tell us much. We need. Actually, you know what? I am gonna do an abstract class. A computer module. I don't want to call it a AI module because that just sounds ick, like double capital A's or something like that. A computer module. Yeah, it's. I can't think of a better thing. Extends a player module. Actually, do we need to do this? I'm not sure that we do. I'm not sure. Maybe. Yeah, let's do it. Let's do it. Now I'm kind of messing with things. You know what? We're not gonna do this. We're gonna get rid of it. Yeah, whatever. We're just gonna do it up here. A player module. Formulate guess. So we're going to make that a protected, and then we're going to do another one. Combination. Formulate guess internal. Okay. So this is going to be combination combo equals formulate guess internal log handler dot get instance dot add log guess combo. Okay, and we're just doing this so we can see what the actual guess is. Now, of course, that means that this is now protected, I believe, and this one is now protected with the funny name. Okay, much better. So now, if we run that, we can see what the guesses are. So this guy is he's guessing randomly every single time, not improving at all and losing every single time. If we go back to the human module just to make sure that it's still working. Mastermind run. RYGB. This is just going to print out your guess every time. RYBG, which is not that big an overhead, and I didn't want to have to do an intermediate. I got my head confused with super methods and abstracts, and it just messed me over. So don't want to do that. Okay, so what we want to do here is we're going to activate the stupid AI module. Run that again just to see what it does. Loses again, of course it does. RYPU, it got close, that's not too bad. So we're going to do some analysis code here. Int game count equals 0, int win count equals 0, int total turns equals 0. So we're going to have to change this a little bit. So this is going to return an int instead. Board.get turn count, return -1. So that's a bit hacky. You're trying to return two different bits of information at the same time. But yeah, you know, it's fine. Turn count equals turn. Not sure if we still need this method. The controller was this turn limit, so technically we don't. Board.get turn count equals mastermind run dot turn limit. Okay, yeah, we don't need that method anymore. Let's get rid of it. Still need the turn limit in here. We'll keep it in there just to be safe. Or do we just remove it entirely? I want to keep it encapsulated. I like to keep this one encapsulated. Although we did remove that method just then. Whatever, game controller. Yeah, it's fine. You're direct referencing it, so I'm happy for this class to keep direct referencing it. Not happy for the board though. I'd like the board to be encapsulated. Okay, back to Mastermind run. Int win turns equals 0. Win turns more than 0. So it's never going to be 0. There's always going to be some amount because the turns always start as 1. Okay, so win count plus plus, and then afterwards game count plus plus, and we only want to increment this on a win. Okay, we don't care about how many turns it took to lose. It's always going to be 10. We don't want that to be impacting us. So let's say system.out.print1 count out of game count games. We have to do some double manipulation here. If you're going to do double manipulation, just make it a double from the start. It makes it easier to deal with later. You can add an integer to a double and it's still a double. .out.println average turns to win, total win turns divided by. Now if you divide a double by an integer, I think it becomes an integer, but I'm not sure. Double turns win turns average equals total win turns divided by. Let's just do this to be safe. So that'll convert win count to a double, and then you got no problems. win turns average. Okay, so we're going to, still using the stupid AI, we're going to turn that false. We're going to run it. 0 out of 1 games. Game controller. We need to make sure that this is a log as well. Log handler dot get in dot get instance dot add log. So we don't want that printed out every time. 0 of 1 games. Average turns to win, not a number. Okay. So never won a single game. Okay. Let's see how we go here. 100 games. Okay, so the only game it won on the first turn. That's pretty impressive. It obviously just got lucky. That time it won 1 game, but it won on the second turn. Okay, let's go a little bit more crazy here. Okay. All right, 5. So that's about average. And I reckon 5.5 is not because it did anything smart. It's because that's halfway between 1 and 10. So that you could see that took a little bit of time to actually spit out. 10,000 games, 6.1, 47. So I'm going to put it up to 100,000. I'm guessing this is going to take a hot second. Yeah. So by doing completely average, the average win rate is 590 out of 100,000. So if we get rid of 2 zeros, that's 5.9 out of, so 0.59% it'll win if it's just stupid. Let's do that as a percentage. System.out. Double win percent equals win count times 1.0 divided by game count. I think that will work. 1%. Win percent. Okay, let's double check that. 0.59. Win chance. Win rate. And then we can do this percent at the end of it. There we go. Beautiful, beautiful, beautiful. Let's take that back down to 10,000. I don't like that little weight going on. It's still 0.62%. Okay, so that's our starting point. That's the stupid module. That's the module that doesn't know what it's doing. So now I do have an algorithm. I did have a look actually on the wiki, and there was a bunch of algorithms that I saw. So if you go to the wiki, you've got the 5 guess algorithm by Donald Knuth. You've got a genetic algorithm by somebody else. You've got a bunch of different things. I'm going to try and approximate the way I've been doing it. So it's pretty much 90% of what Knuth's algorithm is. I hope I'm saying it right. It does start with a K, but I'm assuming that's a silent K. His algorithm is basically start off with every single combination, try a random one, see how it goes, and then eliminate all of the combinations that don't match up with the secret code given what you know so far, and just keep pruning them down and pruning them down. Now, his one is 5 moves or less, but his one is for duplicate colors. We don't have duplicate colors, so our one's going to be a lot simpler because he's got some min-max to figure out what the next guess is, and that sounds complicated as hell. So I'm going to ignore the min-max, but because we're not allowing duplicates, I think we should still be able to go into the five guesses or less, which is what I've been finding when I play it myself. So, alrighty then. What are we going to call this one? Elimination. So this is the simple elimination AI module. And the good thing about putting this, I could have put these as a method, but the good thing about making them classes is you can have local variables to store information and data and all that sort of stuff that you want. Extends a player module. Okay, add and implement methods. Formulate. So we want a list. Viable guesses. So we're going to populate this list with every single possible combination at the start of the game. Come on, don't do this to me. All right, we'll save it again. See if there we go. There we go. So at the very start, I'm going to populate this with all possible combinations. Okay. Now there's no real easy way to do this, is there? So we're just going to have a bunch of for loops, I guess. For token color tk1 dot values See, this is the sort of code that I would get yelled at for writing at work, because indenting this many for loops is not great. It doesn't look great. I mean, we could write a recursive method. You know what? Maybe we'll do that instead, because this many for loops. And if we got an if statement at each level, that's just going to be nasty. So, how do we write a recursive method? Let me see. So, okay. Here's what we're going to do. This is advanced programming. Well, it feels like advanced programming anyway. Animation. Get next token for combo. Okay, now if we write this correctly, this is the only method that we're going to ever need. I think we're gonna have to see how this goes, because this is pretty crazy. Okay, list combination all combos. Yes, this definitely has the potential to go horribly wrong doing it this way, but I still don't like, you know, bloody four for loops in a row. I do not like it. Okay, so this is kind of our template. Okay, this is going to be, so this is the list of tokens we have so far that we've built up. So basically, viable guesses is going to be get next Tom and then a new array list. So we're going to pass in an empty list, and it's just going to build it up. So we've got all our combos. If tokens dot size equals 4, so if it's 4, then that's as far as we've gone. We've got all the tokens we're ever going to get, and there's nothing else to do there. So what we do is all combos dot add new combination tokens and return all combos. So that's fine. So that's if we got to the final one. If the size is less than 4, then what we do is for token color dot values token equals a new token TKC. Okay. If tokens dot contains, because we don't want to make guesses with duplicates, that's just a waste of time. Contains token, then we don't care. We don't care. We're just going to continue on. Otherwise, list token. Very important that we duplicate this here. And I'm pretty sure that it will duplicate it. New array list tokens. I'm pretty sure it'll duplicate it, but just to be on the safe side, we're going to add all here tokens. List dot add to the end. New token. We should probably call that new token, just to make it absolutely crystal clear. And then we call all combos dot add all get next token for combo, and we pass in the new list. And then we go through all of them, and at the end we return all combos. So this is what I call crazy code right here. And it almost warrants commenting here. I think it does. If we have 4 tokens, then finished. Add all combos for each non-duplicated new value to the existing incomplete combination. I feel like that comment almost needs its own comment to explain it. Add all possible token colors for each non-duplicated. Yeah, that's confusing me. Whatever. I think it's good. What we're going to do here is we're going to viable guesses dot size. Now we got 8, but we're not allowing duplicates, so it should be 8 times 7 times 6 times 4. So that'll be what we do. 8 times 7 times 6 times 5. Sorry, 8 times 7 times 6 times 5. So elimination AI module. We're going to set the run count back to 1. And I just want to really... Okay, good. So 1680 and 1680. I'm going to take that as a fairly strong indication. We are going to debug here just to be on the safe side. Viable guesses. Let's have a look at this one. What do you got? RYGO. What do you got? RYWP. So it does look like it's taken the R1s first. It's rolling through all of them. So we go to the end. BYOR. 1600. WBG. WBUP. WBUO. Okay. I'm feeling pretty good about this, because if we... So let's look at token color for a second. So yeah, so WBUP is WBUP. So it is going through them in order, and the first one was RYGO, I think. Yes, it was. Okay, so my confidence has gone way up. What the hell? Exception, null pointer exception. What is this piece of code? Oh, because it's returning a invalid combination. Okay, that's fine. Yeah, that's fine. So anyway, we're pretty happy that that code is working. Get rid of these 2 guys. Alrighty, so that is how you do a recursive method. And Imagine if we did this, you had to put this logic inside 4 if statements. We would have had to, actually, I don't know, maybe it would have been simpler, but whatever. So now we're formulating guesses. Yeah, so what do we do? If board dot get turn count, if it's the first turn, we could return a random one here, or we could return a consistent one. I like the idea of consistent because that's the way I always play. New combination. We can actually do secret code utils dot parse user input red, blue, green, yellow. That's the one I always like to start with. So it's probably going to throw a null point exception at some point. Since we're only doing one run, let's turn the logs back on and see if this is working. So turn 1, guess R, B, G, Y, red, blue, green, yellow. Yellow pin 2, okay, so that's pretty good. And then it gets the next one and it says done. Formulate guess internal. Okay, so what we're going to do here is we're going to have 2 methods inside here. So we're going to have reduce guess, reduce guesses. Yep. And then we're also going to have determine next guess. And the next guess, honestly, we might have to do something in here, which I'm not sure about. What we'll do now is turn next guess. And the next guess for now, I'm going to make something stupidly simple, but it may not work the way I think it should be working. So return viable guesses dot get 0. If viable guesses dot is empty, then we crash. No more viable guesses. This should be a combination. Yeah, we can just do this. Okay, so this reduced guesses is going to be basically destroying this list, removing everything that doesn't match up with the result of the latest evaluation. And since we're doing this every single turn, we're only going to remove stuff that's already in the list. So automatically, this viable guesses is only going to contain the things that have matched all the previous evaluations. So by definition, this will absolutely have everything which matches every single evaluation in the game so far. So this list should be reduced quite a bit. So we're going to do int old. Actually, we'll do it inside the method. Reduce guesses. Int old guess size equals viable guesses dot size. I'll put a bit of a log here. Log handler dot get instance dot add log reduced viable guesses from 2 new guess size. So if we do that now, basically what's going to happen is it's not reducing them at all. Yeah, technically this would be doing it before the turn 2 is 10, but I suppose it's turn 2, you reduce the viable guesses before you make your turn. So that's fine. I suppose that's fine. So this is reducing nothing, which means it's not getting any better. Why is it guessing that? Oh, it's guessing the first thing in the list. So it always gets the first thing in the list, and since we're not reducing the list, then it's not going to be reducing it, or it's not going to be getting anything different because the list is always saying the same. So here's where we get into the interesting bits. And we're going to need to steal some code from the secret code controller here. Evaluate combination. Now, this one uses a secret code map, but I do definitely want to pull this out and pull this in here, which is no longer going to be called secret code utils because we're using it for everything now. So we'll just call it code utils. Generate random combination, and then we make this a static. And it was nice that we had this map in here, but you know what? We can just create it every time. That's fine. Code utils. Evaluate combination. Okay. So we've got to have a secret code here. We're going to rename this. So this is going to be our guess, and this is going to be against the code, secret code. So we don't need this anymore. We don't need this anymore. We still got a secret code, but now the guess. I guess it doesn't really matter which order we're doing it like. So we're going through the secret code, and then we're saying, does the guess contain this? So on and so forth. So this is fine. Secret code controller. We still want this method because we still want this to look nice. But this is basically going to be code utils dot evaluate combination secret turn and turn guess, which we might as well just call guess. Guess is one of those words that you look at it for like 15-20 minutes and you're just like, man, that is a stupid word. I do not like looking at that word. So what we're going to do here is basically we're going to go through every single combination and we're going to treat every single combination as if it was the secret code. And we're going to say, all right, I put in this guess and I get this evaluation. Is the evaluation the same as what I got the last turn for the thing I put in? If the answer is yes, then this is a viable secret code and I'm not going to eliminate it. So what we need to do here is combination bad guesses. This is confusing me, so I'm going to change this to viable secret codes, which technically means the same, but goddamn, it's because. But we're going to be pulling a guess out of the board and throwing that guess against a bunch of secret codes that we get from this array. So I suppose this makes a little bit more sense than. Do we have to? No, I don't think we have to update any of these comments. Okay, so bad codes, bad secret codes in new array lists. God damn, my typing is terrible today. Okay, so for combination viable secret codes, this should really be have an S on the end. Yes, it really, really should. So for the secret code on the evaluation, eval equals code utils dot. We need some information out of the board at this point. So reduce guesses. Okay. Combination last guess equals board dot get last guess. Evaluation last eval equals board dot last evaluation. Keep the methods nice. I mean, the variables, maybe, you know, you can mess around with them, but you keep the method names nice. Get last evaluation. So return, where's that variable? Evaluations dot get turn -1. Might be nice to have a crash log in here as well to say, you know, if turn is 1, then you're going to throw an exception, but whatever. I'm starting to get over it at this point. Although we are in the board, aren't we? We are in the board class, so I feel like we have to be very rigid in here. So if editions dot contains key turn -1, and combination for last turn. Yeah, that's fine. That'll crash and that'll print out all the other stuff as well. Cannot find evaluations. And technically this should be below this, but whatever. Code. So we've got this dot evaluate combination for our secret code with the last guess. If eval dot equals last eval, then bad secret codes dot add secret code, and yes, we've got to change that to a not. Okay, now let's go to the evaluation. We're going to need a hash code and an equals for this. Job's done. So red pin, yellow pin. Okay, so elimination algorithm, basically, and then we need viable secret codes dot remove all bad secret codes. Now, since we're removing stuff, I think we need a hash code and an equals for this guy as well, just to be on the safe side. Okay, let's give that a run. 1680 to 8. Wow. Okay, no, that's fair enough. You got a red pin and 3 yellow pins. So reducing it to 8, I think, is understandable. Reduces it to 4, reduces it to 3, reduces it to 2. Wow. He got it down a lot, but then it's just, ugh. That's interesting. So finally won a game, but man, Mastermind. Okay, this looks a little bit more. So 1 yellow pin. So reduces it to 288. So is that, and then red pin. These are the kind of things that, you know, it's hard to work out if the code is actually doing the right thing. 288 with 1 yellow pin. There's probably some maths behind it that we could do. So it's 288 with 1 red pin and 1 yellow pin. doesn't seem like it should be the same number. I mean, it's finding the correct combination. So whatever it's doing, you know, it's doing a good job. I mean, if it was doing something wrong, look, this is the beautiful thing about this code, okay? I can look at this module and I can say, what the hell is it doing? Is it correct? Is it not correct? Is it doing something stupid? Is it doing something crazy? Is it wrong? Is it right? It's winning the game right now. I mean, it's reducing the guesses, and as far as I can tell, it's reducing them very quickly. 10 to, it's winning the game. Now, we probably could do it a bit more efficiently because it's, you know, it's taken its time sometimes. 6, and our aim was 5. So there we go, 4. So it starts off with 2 and 1. Then it moves to 1 and 2, then it moves to 3 and 0, then it moves to 4 and 0. I think that maybe there's a bit of luck. So let's go ahead and set this to 1,000 and turn this to false. Mastermind run. No more viable secret codes. Okay, what the hell happened here? Now this is really interesting. So turn 1, RBGY, evaluation red pill. That's not good. Yes. Okay. No, that's fair. That's my problem. That's my fault. That's totally my fault. Elimination module. So what we need to do is pmodule.initialize. Okay. We want to create an initialize abstract, which everybody has to implement. This guy is going to do nothing because he doesn't need to do anything. The stupid AI module is going to do nothing because it doesn't need to do anything. This guy is actually going to be using this for something. There we go. So that's beautiful. So that means that this gets created every single time. That was weird. That was very weird. God damn it. Why would you do that? Why would you automatically set it to be, like, I type it in and I say automatically create it, and it automatically creates it and overrides and does all this sort of stuff. You type it in, it automatically creates it and sets it to protect it. It's like you're shooting yourself in the foot, Eclipse. Okay, that's a delay. That's a big old delay. That's a big old delay. Okay, let's turn this down. We have to figure out what's causing the delay, because it's either generating the thing at the start or generating or pulling the eliminations down, eliminating the guesses. So what we're going to do is we're going to eliminate one of those. So default viable secret codes. Viable secret codes equals new array list. Oh, that's not what I meant to do. So we're going to create it once at the very start, and then we're going to just clone it every single time. I wonder if I can actually go. No, do not have the source. I'm not allowed to look into that. Go away. Okay, that was still a little bit of a gap for 100 games. That's not great. We're getting some average turn rates, which is really nice. 5.04, 4.86. I wonder. So right now we're going through every viable secret code and then removing it and evaluating the combination. Now we're not worried about duplicates, so I'm not sure if there's any way we can actually see this secret code map. We're generating that every single time, so that may be an inefficiency right there. So this is trying to make the code faster. Oh, what can we do here? What are these methods doing? Okay, that's pretty trim. I'm not sure if we can do that. Can we get rid of the map? We could front load it in the... No, that's crazy. That's crazy. We want to just be passing in a combination here. So what we really want to know is... Okay, you know what? This is just over the top. This is just over the top, okay? Int I equals 0, I less than secret code dot size. We're still going to make it somewhat generic, but token equals secret code dot get tokens dot get I. Okay, so we'll rename this to index. Yeah, so token. I'm not sure if that's going to speed it up a lot. I have a feeling that it's the stuff inside these ones, inside these methods, that may be doing it. Because I mean, it's string, list containment stuff is not nice. Yeah, I don't feel that. I don't feel like that helped a lot. Okay, but performance notwithstanding. Okay, look, if I run 100,000 games of KDM, it's going to take longer than 100,000 games in here, so I'm still okay. What we could do is that here's the thing about running simulations, okay? If you see the console output and it's not doing anything, then that's bad. So run count. What I like to do here is I like to split these up into two. Okay, actually no. For int series equals 0. And this is just me sort of faffing around at this point. We don't really need this, but I like it. I like doing it. Okay, series count dot out dot print ran. What are we doing? Game count out of series count times run count. It's a little bit nicer. It seems to, it's like a brain trick or something like that. So ran 100 out. See, that's, you're going for 1,000, but because you're seeing them actually spin off like that, it feels like the whole thing's going a little bit faster. But anyway, that's still slow. That's still very slow. Win rate 100,000. How did that happen? What did I do? What did I do? Game count. Well, the turns to win is... What did I do? What did I do? Set this back to 1. Must have done something. Oh no, of course. Of course. Our AI is so good that it wins every game now. Yeah, so if we change this down to 3, we say you only got 3 wins, three turns to go. Now it only wins 6 games. If we set our turn limit to 4, I was surprised because I was like, how is it winning every single game? But then it was like, oh, you know, it's Mastermind. If you know what you're doing, 33% of games. So if we set our turn limit to 5, it's going to win most of them. 73%. And if we set it to 6, 100%? 99%. There's like there's one game that it couldn't win. 96%, okay. Bloody oath. All right, well, you know, within 6 turns it wins 99%. Within 5 turns it wins about 75%. And then, you know, give it 10 turns, it always wins. So I'd say it's doing pretty good. Okay, we definitely want... Okay, I think what we need to do here is we need to have a map of integer to integer turn counts. New hash map. Just so we can see some sort of statistics. This is all the fun sort of analysis stuff that I do for KDM. So if turn counts dot contains key win turns dot put win turns 0 not dot put win turns turn counts dot get win turns +1. And now all we do is dot out dot print line turns because I don't like this average 4.7. I want to know how many times it actually won in one turn, how many times it won in 7 turns. I want to know if there's a 7 turn go that it actually just completely just balled it or something like that. Or balled it is actually good, so something else. Yeah. So we might have to, I think there's some optimization we can make to this, but I think we have gone quite long this one. So I think we'll probably just be leaving it here. What's this going to show us? Is this going to show us the correct? Okay, so it won twice on one turn, 8 times, 50 does, and 600. So it never got more than 600. We did have, well, that's for wins. Obviously, it 97.1%. It lost. Oh, yeah. Well, whoops. That would be why. That would be why. So now we set the turn limit back up to 10, and now this map will give us some more useful stuff. So I'm hoping to see maybe a couple of 7s, but no 8s. If there's an 8, then I'm really worried. And I reckon it's still possible that with no duplicates, we can get it down to 100% 5 and below. That'll be my aim anyway. Yeah, 37s. So that's... No 1-turn victory this time, but a couple of 2 turns. That's pretty good. So most of them in the 5 turn, a little bit more on the 4 than on the 6. So it's pretty good, but it can be improved, I think. It can definitely be improved. Definitely the best possible is like 4.3 with duplicates. So I reckon we should aim for something like that without duplicates. I reckon... I'm not too fussed if we get down to like 4.3. I just don't want to see any 7s. And I'd like to not see any 6s. But then again, who knows? I'm just gonna run this again because I like running it. I like running it. So anyway, that's all good. We're going to be, I think I'm going to finish this off now. And we're probably going to do one more video, and I'm going to go into the, I'm going to go into the elimination thing and rejigger it a bit, or maybe create a new one, copy this code, and then like a smart elimination. Because what I want to do is reducing the guesses is fine, but this determine next guess, where all it does is get the first one out of the list. That's not great. What we really need is a bit more diversity. There's an 8. So let's do a collections.shuffle. Let's do this, because what I want is a bit more diversity. Like this one, you can imagine it's always going to go for the first one, which means it's always going to go for the lowest combination, which is a lot of reds, a lot of blues. If we have a look at the token color, because these are mixed in this order, so it's going to eliminate it, and then it's going to keep going with the earliest ones it can, which means a lot more likelihood to pick red, yellow, green, orange, so on and so forth. Whereas what I do when I usually play it is I try and diversify out. Like if I get 2 yellows, I'll keep red and yellow, but I'll get rid of green and orange straight away, and then I'll go to pick pink and purple or something like that. So a bit more diversification. So let's try that. I mean, it's easy enough. So we've shuffled it. Let's just go for it. Mastermind run. And if this is less, so our previous one was like 4.8, something like that. So this is not great. What we'd really want is something that tries to pull more colors in. So if it picks a code, it picks one with, you know, I don't know, 4.8. It didn't really improve much. Maybe a little bit, but no, 4.8, it doesn't seem to have helped it. So I don't know, maybe my strategy is not that great, because what I usually do is, yeah, I assume that every single one I pick is going to be the one. So if I get a red and a yellow on the start, and it's red, blue, green, yellow, I'll pick the red at the same spot, I'll pick the blue at a different spot, and then I'll get rid of the green and the yellow and replace them for something else, trying to win every single turn. No, it doesn't seem to have improved it. I'm sure we can improve this. Next video though, next video is going to be the one where we do it. So yeah, we'll get rid of that. That doesn't seem to have helped. And yeah, so next video, I keep looking over to XSplit when I think I'm talking to people, but it's actually my camera. So yeah, so next video, we're going to try and reduce it. I have to think about how we're going to do this, but it's better guesses, a better determination of guesses, trying to figure out what the next guess is going to be with a little bit more smarts in it. So anyway, thank you very much for watching. I will be committing this code up to GitHub in the next few hours probably, although it'll probably be up in GitHub way before this video is up. So anyway, thank you very much for watching. I will catch you guys later.